Welcome to our channel. In today's tutorial, we're diving deep into a crucial aspect of debugging in Java, inspecting the call stack. Whether you're a beginner or an experienced developer, understanding the call stack can greatly enhance your ability to troubleshoot and debug your code effectively. So, what is the call stack? Simply put, it's a data structure that stores information about the active subroutines or functions of a computer program. Each time a function is called, a new frame is created and added to the stack. This frame contains details about the state of that function, including parameters, local variables, and the address to return to after the function completes. In Java, understanding the call stack becomes essential, especially when it comes to error handling. When an exception occurs, the call stack provides a snapshot of the active execution flow, allowing us to trace back exactly what led to the error. Let's kick things off by setting up a simple Java program that we can use to inspect the call stack. In this code, we define a class named callStackDemo with a main method. The main method calls method A, which in turn calls method B, and method B calls method C. Finally, method C throws a runtime exception. Now, let's run this program and see how we can inspect the call stack when the exception is thrown. Now, if you run this code, you'll encounter a runtime error. But don't worry, that's exactly what we want to see, as it's going to help us explore the call stack. Take a look at the console output. The output will display something like this: exception in thread, main, java.lang.runtime exception. This is a test exception. Below this line, you'll find the stack trace, which is our call stack in action. Each line in the stack trace indicates a method that was called leading up to the exception. Let's break it down. The first line shows the exception that was thrown. The next lines provide the sequence of method calls that were made. The last called method on the stack is typically the one where the exception originated. In our case, we see that method C was the last method called before the exception occurred, followed by method B and method A. This call stack is extremely useful for debugging. It helps you track down where in your code the error originated and how the execution flow reached that point. But that's just the start. We can also programmatically retrieve the call stack within our Java code. To demonstrate this, we can use the thread.currentThread.getStackTrace method. Here, we've added a new method called logStackTrace, which retrieves the current stack trace and prints each element. Now, before throwing the exception in method C, we'll call our logStackTrace function. This way, we can log the call stack before an exception is thrown. Let's see how it works. When we run this updated code, not only will we see the exception thrown, but we will also see a complete log of the current call stack leading up to that point. This is a helpful addition for debugging, as it clearly shows the flow of execution before the error occurred. The output from logStackTrace will show you something like this: java.lang, thread.getStackTrace, thread.java, 1556, callStackDemo.methodC, callStackDemo.java, 14, callStackDemo.methodB, callStackDemo.java, 10, callStackDemo.method callStackDemo.java, 6, callStackDemo.main, callStackDemo.java, 3. Each entry in this log provides details about where each method is defined and at what line number, making it easier for you to pinpoint where things went wrong. The stack trace includes class names, method names, and line numbers, all crucial for a developer trying to debug an application. But wait, there's more. In addition to retrieving the current call stack, it's important to know how to manage and manipulate stack traces. You can customize exceptions with meaningful messages that may include status from your application state. This is particularly useful in larger applications where context is key. In the above updated method C, we wrapped our exception throwing in a try-catch block. This allows us to catch the exception and print a custom error message before printing the full stack trace. This can give you context on where the issue originated and additional details that could help in debugging. Now that we've explored inspecting and manipulating the call stack, let's discuss some best practices when it comes to debugging with the call stack. First, always read the stack trace carefully. The top of the stack trace indicates where the error occurred, while the lower entries provide context on the call flow. Second, try to include meaningful exception messages in your code, especially when throwing exceptions. This extra information can provide context that might be necessary to understand what went wrong. Additionally, consider logging stack traces to a file or a logging system, as this can be invaluable when diagnosing issues in production environments. Also, remember that the call stack can quickly become large with deep method calls. If you notice performance issues or excessive stack depth, you may want to re-evaluate your method structures and possibly refactor to flatten the call stack when appropriate. Lastly, practice makes perfect. The best way to get comfortable with inspecting the call stack and debugging is to actively practice in your projects. Create code that intentionally produces errors and practice reading and navigating through stack traces until it becomes second nature. To summarize today's tutorial, we covered what the call stack is and its importance in debugging Java applications. We looked at how to programmatically inspect the call stack, customize exceptions with meaningful messages, and best practices to follow when debugging. Thank you so much for watching. If you found this tutorial helpful, please give it a thumbs up, subscribe to our channel for more programming tutorials, and don't forget to hit that notification bell to stay updated on our latest content. Until next time, happy coding!